It's a big pleasure for me to introduce Ezra Getzler, who is telling us about the homotopy moment map for Chern-Simons field theory. Thank you.
Yeah, okay. Thank you very much. I'm so excited to be at this conference and at Amherst, it's pronounced. Yeah. So the title of the talk is very controversial because so if you've read Christoph Bloemann's paper, he emphasizes that moment is a mistranslation of the French and that it's really the correct word in English is momentum. So that's the first controversy. It's not so much a controversy as, in my view, the word homotopy is completely redundant. So I think what the authors that I'll be telling you about had in mind was that the momentum map was just the top piece of the thing that I'm going to be telling you about. But I'm going to present the view that it's the whole package, which is the object of study. So this is just an exercise in rearranging the definition of homotopy momentum map so that it looks, I don't know, it fits better into the world of pre-quantization. That's the goal. Because as many of you know, what is the moment or momentum map? It's essentially the lift of a Hamiltonian action or a symplectic action to the pre-quantization line bundle. So this is sort of the perspective that lies in the background of my talk. The test example is going to be a classical field theory, Chern-Simons field theory. So that seems to be everybody's test theory for classical field theory problems. And classical field theory is not exactly symplectic geometry. That's the part of the point. So this is a sort of more modern version of Emmy Noether's approach to classical field theory. So
I'm so sorry.
This is going to happen again and again.
I'll be here to troubleshoot.
Yeah. Okay. So the announcement that we were alluding to is that my university, Northwestern, will host next year's Gone Fishing Conference. So I don't know, and that's really convenient. We're right near 2 airports. So, well, actually, you're just as close to Hartford Airport as we are to,
yes.
as we are to here. So I shouldn't exaggerate. Yeah. Okay. It's just it's in a different state. Our airport's in the same state. Okay, and the same time zone and everything. Okay, good. So, so we're going to talk about n multisymplectic manifolds. So we have a natural number n. This will be the dimension of the world sheet. So in ordinary mechanics, it's 1. And in Chern-Simons theory, it's 3. And so an n multisymplectic form is just a closed n+1 form such that the contraction with vector fields has no kernel. So, so then, incidentally, the Hamiltonian vector fields are the ones such that the contraction with this n+1 form is an exact n form. And so then the momentum in the most naive sense is just an n-1 form. And you can see that there's, instead of the ambiguity in momentum being a constant in ordinary symplectic geometry, it's actually a closed n-1 form. That's a big ambiguity. And that's where the homotopy in the title comes from. So, and the case n=1 is very special because that map from vector fields to 1 forms, at least if the manifold is finite dimensional, is a bijection. But that's unique to the n=1 case. So throw that away. And it's related to the previous remark I made. So, so I'm going to have a Lie algebra, H, which is acting on my n multisymplectic manifold. So it acts on the manifold, first of all, by a homomorphism to the Lie algebra of vector fields. And those vector fields preserve the differential form. Okay? So let me introduce the Chevalley-Eilenberg complex of the Lie algebra that's the symmetries. And I'm assuming, unfortunately, that you know the Chevalley-Eilenberg complex and its differential. The differential raises degree by 1. Just like the Rham differential raises degree by 1. And in fact, they're given by the same formula, basically. So if you know the formula for one, you know the formula for the other. So we'll tensor those two together. So we now have a double complex. And I can, just for convenience, let's choose a basis of the Lie algebra and a dual basis. And then we have this operator which captures the action. It does the contraction of vector fields on the de Rham side, and it does the multiplication by a ghost, if you're into field theory, on the Chevalley-Eilenberg side. And the total, that combined operator is degree 0 in total degree, okay? So that's a fundamental operator that was introduced, well, maybe it goes back to Hochschild or Chevalley and Eilenberg, but it takes the key role in the paper of Callias, Frégier, Rogers, and Zambon, in which they introduced the homotopy moment map. So here's the formula. I'm going to use delta sub 0 for the differential in the Chevalley-Eilenberg complex, because later we're going to have Chevalley-Eilenberg with a H module. And then we'll have the total differential for that whole action. That will be delta. So here's the formula that they give for what is a homotopy moment map. This is a little rewritten from their formula. I think I'm observing that their formula actually incorporates the exponential of this operator iota. They wrote it out in multi-indices, and so they didn't notice that they had an exponential, or at least they didn't write that they noticed that they had an exponential. So what are we doing? We're rotating the multi-symplectic form using this iota. So, and then we're subtracting out the multi-symplectic form. So we've got something which is now of strictly positive degree in the Chevalley-Eilenberg direction, and a homotopy moment map is a something whose total differential is that thing. Okay, so, and guess what? Okay, here's an exercise that please do after my talk. For n equals 1, check that this is nothing more nor less than the usual definition. Actually, I say that on the next slide. So I'll skip this because time is short, but hopefully will we be making slides available?
Yes.
Yeah. So I also don't give all the details on this slide, but a good exercise to complete the calculation, and you'll see that you get exactly the usual definition of a moment map. So this is weird. I'm very dissatisfied with this perspective on momentum, because for me, momentum is more, having trained with Berlin and Verne, momentum is more about equivariant differential forms for some group action. But that's really for a proper group action, I think. Somehow, in the more general case, you should be combining equivariant differential forms and this. It's some sort of Van Est story. So I don't know the final answer, but maybe this needs to be a bit upgraded to the correct definition of momentum. I'm not sure. So, yeah.
So the equivariance is contained in the next step, right?
It's somehow, it's contained in the statement that iota squared of omega is 0. Yeah, because that's a 0 form, and so it can't be exact. Yeah, so it's a really sneaky. Yeah. Oh, sorry, you're right. Yeah, and then that's delta 0 of iota omega. So it's just so the secret. If you read their paper, you'll see that they've rewritten an idea of an L infinity morphism from H to Rogers's L infinity algebra, and then it's completely clear this calculation in that setting. So, but I'm throwing away L infinity morphisms for this talk and just sticking to sticking to that formula on the bottom line. So now let me rewrite that formula. That's the main point of this talk. So I'm going to rewrite the formula for exact multisymplectic manifolds. So I'm going to assume for now that my multisymplectic form is exact. Well, that's certainly true locally. And if you know the situation, you'll know that in the usual case of symplectic forms, gluing together those local choices is exactly the construction of a line bundle with connection. And those local choices of one forms are the connection one forms of this line bundle. Well, once you multiply them by I. So, because it's a ideal, well, anyway, it's a complex line bundle with Hermitian, no, that's nonsense. Sorry. Okay. I hope this isn't recorded. Oh, no. Okay. Yeah, thank you. No, you won't. So what we're doing is the local story for now. And on the very last slide, I'm going to tell you that we should upgrade everything I'm going to tell you for differential characters. And that's going to be the perspective that I'm proposing for what homotopy moment maps is. Now, the odd thing is that for ordinary symplectic manifolds, again, it gives you the usual story. It doesn't change anything. So it's always important to double check that we haven't accidentally broken our understanding of what a momentum map is in n=1. Okay. So I'm going to replace just the tensor product of these two complexes, the Chevalley-Eilenberg and de Rham, by a twisted tensor product, which if you've studied Lie algebra cohomology is very familiar, that the differential forms form a module for the Lie algebra with Lie derivative as the action. And so the tensor product has a twist, which is given by the second term in that formula, which is just capturing the Lie derivative action. So now we have everything glued together, and my reformulation in the case of exact multisymplectic manifolds of the definition of homotopy moment map is going to involve this, to me, much more natural complex. So here's a little lemma that is basically Cartan's homotopy formula for the Lie derivative as the commutator of the de Rham differential with the contraction. And so it turns out that these two differentials are conjugate to each other. There are a lot of places in mathematical physics where we see analogous formulas to this. So what that means is I can now untwist the formula of Callies et al. And get a much more neat formula in the special case of exact multisymplectic manifolds. So here it is. So notice if I add alpha, which was the n form whose differential is our multisymplectic form, to the moment, the homotopy moment of Callies et al., then we get, I've restored that missing omega in the original formula for the homotopy moment map. Okay, and now I conjugate, and in terms of nu, which is the action of e to the iota on this total sum, and notice there we're getting actions of iota on that alpha, and that should be familiar to you from Noether's work. So the momentum comes in two pieces. One comes from the differential form whose differential is the symplectic form, and which is the Lepage form in classical field theory, and the other part comes from something else, and that something else is nu. And I'm going to call that the homotopy momentum map on the understanding that I have a differential character in the background, okay? That I've lifted my multisymplectic form to a differential character. That's the logic of the talk. And of course, oh, I'm on time. Okay, so that's the definition of a homotopy momentum map for exact multisymplectic manifolds. So that was the purpose of this talk. You can now stop paying attention. So I'm going to work out an example of this now in variational calculus. So I have to do a crash course in variational calculus. Hopefully some of you have seen this, otherwise it's going to be a bit steep. This percent. But the basic idea is that we do calculus on a fiber bundle, except along the fibers, we also have partial derivatives of the vertical coordinates. So the vertical coordinates we think of as the fields. They're the dependent variables. The coordinates in the base are the coordinates of our world sheet. So they're time and space coordinates. And so field theory, which is our modern, it's simply a light rewrite of what Emmy Noether did. We can copy this formula, and that's what I'm going to do. So I'm going to basically drop the variational bicomplex of variational calculus into the slot which was occupied by the de Rham complex. That's the second half of the talk. Okay. Sorry. So sorry. Let me call my coordinates in the base T1 up to Tn. So if we're doing mechanics, they'll just be n equals 1, and we'll just have time. If we're doing gravitation, then n is 4, and these are the time and space coordinates, okay? And then the vertical coordinates, U1 up to U capital N, they're just labeling the fields, if you like, of the theory. And of course, ultimately, they can have Z grading, they can have internal grading, Z mod 2 grading, and be even or odd. We can have some graded supermanifold. But for now, I'm just going to have a manifold of fibers. And let me whisk ourselves through this. Well, so let me denote D partial sub mu. This is going to be crucial. The partial derivative with respect to the independent variables. Okay, and I'm at the bottom of this page. You see partial sub I, capital I. The little I will label which coordinate which field I'm taking a derivative with respect to, and the capital I is which partial derivative of that field. So I is a multi-index for the n independent variables. So all those are called they're coordinates on the jet space of the fiber bundle. It's an elegant, very completely coordinate independent construction, but I've got to move on. So any questions about that? That's a heavy, that slide has twice as much information as you're allowed on a slide, but it's time to move on. This is like, I'm doing all of first year calculus on one slide. Okay, so let O sub infinity be the sheaf on M of functions in these variables. They depend, any function locally only depends on a finite number of the variables. That's part of the definition of O infinity, but let's move on. The main point is O infinity is a sheaf of commutative rings, a lot like the sheaf O of smooth functions on the manifold. So we're now ready to do calculus, variational calculus. So the variational de Rham complex is just the de Rham complex of O infinity. So you've got some generalization, if you like, of the de Rham complex when you have a fiber bundle. And it's bigraded. There are horizontal differentials, which are just the differentials of the independent variables. And the vertical ones are given by this particular formula. I think they're called the Cartan something. Yeah. Okay. So you can split the differential. I'll zip along here. You can split the differential into horizontal components and vertical components, and they both have square zero and anti-commute with each other. Okay. So it's a double complex. That's why it's called the variational bicomplex. So this is the modern, it developed in the 70s. Several authors developed it more or less simultaneously, this formalism. And one of the main theorems in the subject, incidentally, is that the horizontal differential is exact as soon as you have at least one vertical differential. So what we say is that in the variational bicomplex, all the rows except the bottom one, and when I say exact, I mean except for the rightmost slot. Okay, So that's implicit in what I'm talking about, and it's sort of the ultimate generalization of what Noether did, but we have to move on. So a Lagrangian in this language, and this is the justification for thinking about multisymplectic manifolds, a Lagrangian is actually an n-form because it's a density. It sounds like it's a sort of strange thing to be emphasizing, but the reason we want to think of it as a density and not as a functional is because then we're keeping more track of all the partial derivatives we have to perform in our variational calculus. And those partial derivatives obviously have boundary terms. So if you want to keep track of what's happening at the boundary of your worldsheet, then working in the multisymplectic formalism has a better chance of success. And the other reason that you want to keep track of the partial derivatives is they're the origin of Noether's symplectic form on the field space. So we're going to see that symplectic form next. We take L, it's an N0 form. It has N horizontal and 0 vertical indices. And we're going to add another term to it, which if I have a single adapted coordinate frame, is given by an explicit formula. So it's called the Lepage form. This has been generalized to higher order Lagrangian densities, to fiber bundles with a cover by adapted coordinate charts and a partition of unity. You won't find that in the literature because that's in an unpublished paper of mine. But one of these days I'll show you the formula. So in short, you get the original Lagrangian density and an extra term involving partial derivatives of L with respect to the first derivatives of the fields. So it doesn't actually, it's given by a very explicit formula in this local coordinate system. And so you get an N0 form and an N-1 form. And the perspective of variational calculus that I'm giving you, which is the one that emerged in the 70s, is that this combination is the real Lagrangian. The original Lagrangian density is just encoding this whole package. And really, when we specify a field theory, we should write down this whole package. Now, that's my alpha. So there's no accident that it's an n form, and its differential is exactly Emmy Noether's symplectic form, or the density, I should say, of her symplectic form. So that's the formula. There are two terms. The first term is an N1 form, and that's the Euler-Lagrange equation. So So the region where that vanishes is the Euler-Lagrange locus, the solutions of the classical field equations. The second is the density of Noether's form, and notice that's an N+1 form. Okay. So we now can write down the analog of the Cartan formula. So we can study, but using vector fields, which are derivations of O infinity, they can move us both in the worldsheet and vertically. So, okay, I'm accelerating. So, all right, so I just copy everything I did, but in the variational setting. So I think actually I can move on from that slide because I think it's clear. So let me rush over the Chern-Simons story. So the issue with Chern-Simons is going to be entirely whether we have a single chart in the world sheet, which is a closed-oriented three-manifold, or whether we have several charts. So we'll have one chart if the principal bundle can be trivialized. And that's true if the structure group is simply connected. But if you have a compact Lie group which is not simply connected, then in general, the principal bundle will not be trivial. And then we have to use several charts, and that will bring in differential characters. You can't write the Chern-Simons action as a single action on a single chart because the Chern-Simons action is not gauge invariant, unlike the Yang-Mills action. So you have to write it as a Czech cochain. We need, or maybe as a Tom Whitney cochain, and we have to somehow globalize the theory of variational calculus. So the point of my talk is that that is the right context to do the homotopy moment map. I've got 30 seconds. I'll show you some formulas. So this is the formula for the symplectic form for Chern-Simons on the bottom line. So the first term is the Euler-Lagrange equation that just says the curvature vanishes. And the second is just the inner product of the vertical differentials with themselves. So it's if you've read any papers on Chern-Simons, you've seen that symplectic form. I guess it's, anyway, yeah. I'm stuck.
Interesting.
I get an extra minute.
You get an extra minute.
I'm a tough negotiator.
That was not planned, but let's see. Oh yeah, you can move now.
All right,
Yeah.
thank you so much. Yeah. Okay, so so the symmetry algebra will involve both vector fields in the base and gauge transformations, and I'll call that the Atiyah-Lie algebra. I don't have time, unfortunately. So that is the formula for the action. So it incorporates the horizontal action, and then of course it has to incorporate some action on the fields. And it's given by this very explicit formula. I want to remark that this formula globalizes. If you look at the bottom line, you'll see it only mentions things which have which do not depend on the choice of a local trivialization. And okay, and that's the formula for the homotopy moment map for Chern-Simons. So lambda there is, it combines the vector field psi, which is moving us around the base. We contract that with the symplectic, with the connection form, and add that to our gauge parameter. And then that somehow combines into the connection form as a kind of Chevalier-Eilenberg modification, and you just copy the Chern-Simons action. And I don't know, it's a longer calculation at the moment for me than I wish. It takes a page. It should be instant. And so somebody should come up with the reason why this is obvious. I feel like if I just applied e to the iota nu and subtracted omega, I would get mu. I suspect mu might in fact be globally defined, but on the next slide, I suggest that it isn't. So I don't know, the jury's out on that. I haven't done the calculation yet. Whether there is in fact a globally defined homotopy momentum map in the sense of Callias et al. There could well be, but if not, then this would be an example of a homotopy moment map which cannot be written except using differential characters. And so then in that case, I'm not going to write it out, but certainly the Lepage form has to be a differential character in the case of full generality. And then we can take the Chevalier-Eilenberg in the Czech cochains in the variational bicomplex. And finally, we get the location where the homotopy moment map should be. And thank you very much.
Thank you, Ezra. Are there any questions? Oh. The microphone is,
okay.
is going.
I could walk up to you and use it.
Thanks for inspiring talk. This comment that you're making about the differential characters and the globalizing the picture, shouldn't one be working with a higher principal bundle? Like,
well, yeah, I mean,
then,
but it's abelian, remember?
Right.
I mean, unless you have some principal bundle already available, then higher homotopy groups are all abelian.
Right, but it's like, you know, if you start with the 2 form and it satisfies the pre-quantization condition, you get an S1 principal.
But that's exactly what I said on the last slide.
Right, but now
so that differential character is exactly what you're saying. They're the same thing.
Right, but you could try to globalize your picture by constructing an N principal bundle.
I just did.
Where
that's what
where the structure group now is a N shifted. It's like NS1 group, you know, it's like.
Oh, so you want me to glue the group G in degree 1 to the group U1 up in and have a non-trivial homotopy type. It could well be, but the thing is that there'll be Postnikov invariants in that situation, and then we have to do the theory of smooth Postnikov invariants. And I guess the only paper I know on that subject is Enriquez's in Compositio on higher groupoids and L-infinity algebras. And so I think what so the strength of your suggestion would be that by gluing all of that together, that we capture perhaps a generalization of Chern-Simons theory. And I don't know whether that generalization exists. My guess, somehow physicists explore every possibility. So if it existed, we would have heard a rumor of it. But so that's, but okay. I don't know such a formalism, by the way. That is, I'm very uncertain how to construct an extension of a principal bundle by a, I mean, the irony is that my grad student did exactly that, constructed a string principal bundle in a finite dimensional model, Jesse Wolfson. So this would be a higher general, that would be the two-dimensional story. So, yeah.
Right. Perhaps we have time for one question, and then the other questions we can move on to during the break. Thank you.
Again, about the globalization. So in the N=1 case, you see that the globalization naturally leads you to the connection, right, whose curvature
exactly.
is symplectic form. And this already more or less moves towards a pre-quantization bundle. Does a similar story exist in the higher end case? Do you see what quantizations
in a way, because what we're saying is if the fibers, if the space-time is compact, then you can integrate differential characters over oriented. So there's a push forward formalism. It's more complicated than integrating differential forms, but let's say it's as complicated as the definition of the Poincaré of integrating singular cochains over an oriented triangulated space manifold and integrating differential forms. So it's complicated, but that's where the pre-quantization line bundle for Noether's connection on the space of flat connections comes from.
Okay.
Yeah. And then, of course, what I'm describing is the gauge action on that. Yeah.
All right. Thank you again. And let's thank Ezra again.